In the previous session which we started yesterday, we started learning what is performance and how is performance important. I took an example of a car like this and we started analyzing the features of the car. Car 1 had the CC higher, the highest speed a better one, economy was a poor one, gears it had more number of gears, and safety features it had better one, maintenance it had poor features. So then when we have to compare, we need to compare in such a way that we analyze each and every feature of it and then conclude which is the best one. For example, if you want to go with analyzing the safety features, I'll say car A is the best one. If you want to take up the maintenance features, I'll say car B is the best one. So when you have to compare two computers, you need to compare it not with, you need to compare it with all the features traditionally to say like this is the best performing one and this is not the best performing one. So we have multiple things to be including it in this analysis, and one such example I gave you is with the PC called Sachin and Sehwag. Sachin had to run a particular program and he ran it in 10 seconds, for example. Sehwag ran it in 12 seconds. So who is the best? As I told you, Sachin is the best. Sehwag trails by 2 seconds. So we discussed all this and then we went for a small example where we understood that adding a processor which is of high version, which is of higher version and better speed. For example, I have a 4 gigahertz processor right now and I change it to 8 gigahertz. So obviously what will happen? It will increase my throughput as well as it will decrease my response time. Response time will be reduced and throughput will be definitely increased. And the second option which I was talking about is we'll have 4 cores there. I have core 1, core 2, 3 and 4 and I have multiple tasks here. So the every individual task, for example, these tasks will not be run at a faster rate. This if needs 10 seconds, it will need only 10 seconds even now. But since multiple tasks are running parallelly, the overall throughput will definitely be increased. And what we need to understand is if there are queued up, if there are multiple tasks which are queued up, the time will be dependent like that. So it will need time for, if the throughput is more, if it can process more, the time it is required to handle this will also come down. That's what I meant yesterday, as when the throughput goes higher, obviously the response time will also be bettermented. So I have 4 processes here. These 4 are completed. The next 4 will be taken in faster. So the response time for this handling this would also be bettermented. This is what I conveyed you yesterday. Now, I took an example of an athlete who runs a particular distance with 10 millisecond speed or 10 second speed. When you give glucose, he runs it by 8 seconds. So we need to understand what is his performance. So I also discussed that and I hope you understood it clearly. Now let's get into the core part of it. Give me 1 minute, please. Give me 1 minute. So as we discussed, what is performance? The performance is nothing but 1 by execution time. So we need to know the execution time properly. And once we get the execution time, we can derive the performance and it is 1 by T, 1 by execution time. Now what do? We can compare the performance of two different things and we'll get to a factor called N. This N is the factor which can let you know how much A performed better or B performed better. This is what I told you yesterday and we took an example of Sachin and Dravid, and Sachin completing a task in 5 seconds whereas Dravid completing the task in 15 seconds, and on seeing it you can tell that Dravid is 3 times slower or Sachin is 3 times faster. But we need to go by the formula, and the formula is nothing but A's performance by B's performance, execution time of B by execution time of A, which will get you N. So 15 by 3 will get you, 15 by 5 will get you 3, and that's the N. Do you understand all this till now? I think it is easy up till now. So we'll go ahead with the next topic which we have to complete it today. So how do you measure the performance of an embedded system? Now in the last semester we learned what is an embedded system. Embedded system is always a combo of hardware plus software, right? So we need to be careful, and this thing is going to do some dedicated task. I'm going to do some dedicated single function task alone. So for example, the projector, the washing machine, the pacemaker, all these are embedded systems that are going to work on. Yeah. Now when we talk about embedded system, we know that it is going to perform a single task repeatedly and it is a combo. It is a combo of the hardware plus software, and we have been talking about it for a long time and I don't want to waste time again on that. Now, what is the performance metric that you will look into whenever you are analyzing an embedded system? The question is simple. What is the performance metric that you will look into when you are analyzing the embedded system. Right. So the point is simple. We need to look into real time. So real time behavior is the most important component that we need to look into it, because all embedded systems are expected to give you a real time performance. What do you mean by real time? I told you this, meeting the deadlines every time without delay is called real time. We have analyzed this a lot of times in the classes also. What is real time? Logical correctness of the operation within a deterministic deadline. The car braking system, the aeroplane landing gear system, all these are the best examples that we need to consider towards understanding what exactly is real-time behavior. Now, this real-time behavior is the performance metric for any embedded system, and in case you get a question which asks about an embedded system performance, and if you are asked to compare to embedded system performances, the only thing that you need to look into is how much real-time was it, how much accurate it was every time, how much perfectly it has completed the task every time is the most important component that you need to understand. So the performance metric for embedded system is always real time. Remember it. This is a very important question. Now we are going to go better and we are going to understand more in terms of CPU execution time, in terms of CPU things. So we are going to learn that. What is that? Very simple. The first thing that we need to learn is CPU execution time. It is also called as CPU time. We can name it as CPU execution time, or it is known as CPU time also. Now, what is it? Very simple. The amount of time the CPU spending towards completing a task is called the CPU execution time. The amount of time the CPU spends on a particular task is called CPU execution time. Remember it, it's a very important definition. What is CPU execution time? Now, the CPU is not just executing the tasks that you have given it. Remember it, you are running a code, for example. You are running an addition program called add.c. Is it the only task the CPU is running? Not at all. Not at all. It is also running parallelly multiple tasks in the background, and you you should understand that they are called the operating system tasks. The tasks are nothing but the OS tasks, or it can be the CPU tasks. The tasks that we can align with or connect with CPU could be the tasks that you have made it run, or the tasks that OS has given it. Parallelly, multiple things are running in the background, right? So it is called as OS task. And you should understand one point: the system CPU time, the time that is spent for the OS is called as the OS related tasks is called as system CPU time. The time that you are spending for your task can be right away called as CPU execution time, but normally whenever CPU task execution time, but whenever you talk about the total time is always connected to the CPU execution time for the task and OS tasks. The OS task could run in the background. It could be a daemon process. It could be anything. CPU task is something that you have allocated. Add.c, sub.c, mul.c, or some application when you are running. That will be the point. Now, do you understand what it is? The CPU execution time is nothing but the amount of time that the CPU spends on completing a particular task. Remember it. And the second point is CPU not only runs your task, it also runs multiple operating system tasks in parallel for it to survive and for it to complete other things that are running in your machine that you may not be aware of, but CPU still spends time there. The time that it is spending for the operating system related tasks is called as system CPU time. Remember it, it's very important. All right. Okay, we'll get into the next one. Understand what is a clock cycle. I have been telling you this for a long time. Again, we have discussed this in the previous semester as well. We had some discussions on this, I believe. And now, how do you measure speed of a machine? How do you measure speed of a processor? We normally say that it is in gigahertz, and we say that it is 8 gigahertz speed. It has got 4 gigahertz speed. Like that, we are normally telling. Okay. So, what is it? It's very simple. It is nothing but speed of a computer. It is the speed of the processor. We can also connect it to clock cycle. The amount of time that is spent between two pulses. You can see that here. The amount of time that is spent between two pulses. One is high and low. You can see that here. That's called a clock period. And unit of clock cycle is hertz. That's why we normally call it as gigahertz. and you can see that it started with 3 megahertz in 8085. It was all 3 megahertz in 8085. That started growing. Now we are in the speed of say 8 gigahertz, 10 gigahertz, like that we are going. Now understand the point. We have got three terms to be understood here. The first terminology that we need to understood is the clock period. The clock period is nothing but the amount of time that we get from here to here. And we have got clock width, the pulse width. This is called as clock width. And this is called as the rising edge. We have used this in the D flip-flop. I told you whenever the clock is in the rising edge and if the input is coming, that input will be transitioned. I have been telling that repeatedly. So this is called as rising edge. Whenever the clock rises from 0 and it gets to 1, it rises from 0 and it gets to 1, we call it the rising edge. Whenever it falls from 1 to 0, we call it falling edge. Remember it, these two are very, very important. And typically, we need to know all these terminologies for our complete learning that is going to happen right now. So understand all this. We learned what is a clock period. We learned what is a clock cycle. The clock width. We know what is a falling edge, a rising edge. All these are going to play a vital role. Now, when you have a 2 gigahertz processor, we need to understand that it has got this many clock cycles per second. That's why we call it 2 gigahertz. The number of clock cycles per second is what is going to determine how much is your speed of the processor. 2 gigahertz or 4 gigahertz or 8 gigahertz or whatever it is. Now, remember, we have rising edge is the term that we are using quite frequently. It is also regarded as positive edge. In your question, I can also call it as positive edge. And similarly, falling edge can be called as, I can call it as negative edge. It depends, but most of the cases, I call it as a rising edge and falling edge properly. So don't worry about it. Now the terms will be rising edge and falling edge. That's just to let you understand that we can also call it at times as positive and negative edges. So you need to remember it. If the question does not have the term rising or falling, don't get confused. It is okay to call it as positive edge and negative edge. At times people call it that way also. Now, what is the next thing that we are going to learn, sir? Please understand, we have a new formula now that we need to memorize and remember. We need to also understand what is it. CPU execution time. That's what I told you some time back. What is it? It is nothing but number of clock cycles for a program into clock cycle time. Number of clock cycles that we need for running the program into clock cycle time will get you the total CPU execution time. You should not forget this at all. This is most important. CPU execution time can be calculated by multiplying the number of clock cycles into the clock cycle time. The number of clock cycles per program into clock cycle time. Now, it is very important to understand that clock cycle time is nothing but inverse of, clock cycle time is nothing but 1 by clock rate. So, we can make it as 1 by clock rate. So, we get it as number of clock cycles for a program by clock rate. And now with this formula, we can do a lot many wonders. I'll tell you what are all the possible questions, what are all the possible cases that we can handle through this. I may give you the question where we have only CPU execution time and clock rate. I can ask you to find out this. I may give you these two and I can ask you to find out the clock rate. So these kind of questions will be in volumes and you may have to solve all of them. So remember this formula where we derive the CPU execution time, which can be found out by using number of clock cycles for a program by clock rate or number of clock cycles per program into clock cycle time, will be very important, and we are going to remember it and we are going to use it continuously. Let's see a program. I'm going to see let's see a problem which is going to be very interesting as well. So let us go through step by step, and these questions are very, very important. So please remember, there can be a lot of questions of this sort. I am taking Sachin again. There is a program by name Sachin. We have a program running by name Sachin. Now, Sachin runs at the speed of 10 seconds. Remember it. Sachin runs at the speed of 10 seconds, which means the CPU time required for Sachin to run is 10 seconds. Do you understand this point? Sachin requests 10 seconds CPU speed. Now, the clock rate is nothing but the speed. You could not have understood it last time when I call it clock rate. Now you can understand it. The processor speed is nothing but the clock rate. It is 4 gigahertz. Now he needs CPU time of 10 seconds and he needs 4 gigahertz speed. This is the speed of the machine that he has. Now this is the guideline that they have given, or the features that are described in the question. Now what is the challenge and what is the question? This is computer A. This is computer A, where Sachin runs in 10 seconds and he uses the 4 gigahertz. Now, the challenge is to design a computer B. We need to design a computer B where Sachin is expected to run at 6 seconds, and we need to now find out what exactly is the clock rate. But they have given a question with an option. Please find that increase in the clock cycles by 1.2 times. This change, which makes Sachin run in 6 seconds, demands a change in the clock cycle to 1.2 times. Do you understand the question? Let me repeat it otherwise. I'll repeat it once again so that you can understand it clearly. There is a program called Sachin. This guy runs in a machine A which has got 4 gigahertz speed at 10 seconds. Now this guy has to run in a machine B. We do not know what is the speed, but he has to run in 6 seconds. And they also said that when Sachin has to run in 6 seconds, there is a change that has to be done in terms of clock cycles, and it is nothing but it will go to 1.2 times. That's it. Now we will have to find out this particular thing which tells you what is the clock rate for scenario B. Do you understand the question, all of you guys? Do you understand the question? Can I go ahead with the answer? Anybody who cannot understand the question? Is there anybody who cannot understand the question? Please, I will repeat it. Can I go ahead? Only one answer is coming. Now, let's go and derive the answer for this, and let's find out how exactly this can be done. Very simple, yet please watch it carefully. CPU time is nothing but the formula is already declared CPU clock cycles by clock rate. Do you remember this? I told you this a few slides back, and it is nothing but clock cycles by clock rate. Now I make it CPU time for A, CPU clock cycles for A by clock rate of A. Now CPU time in the question itself, they made it very clear. Sachin needs 10 seconds for running in machine 1. Right? That's what they have given in the first machine. So 10 seconds is equal to CPU clock cycles by clock rate. What is clock rate? 4 gigahertz, that was given in the question. So it is done. Now to find the clock cycle, I need to multiply this by this. So what will I get? I will get 40 into 10 to the power of 9 cycles. This is nothing but CPU clock cycle. I have got the CPU clock cycle derived first for A. I am taking the process A and it is done. Simple. I use the formula CPU clock cycles for A by clock rate. CPU clock cycles is unknown, but I have the CPU time here with me, and then I can use it with the clock rate, which is nothing but the speed that I have been specified in the question. So I multiply these two to arrive at CPU clock cycles A. Do you understand this? Now let's go to the next one. Calculation B. I am going to do the same calculation for computer B now. CPU time B equal to CPU clock cycles B by clock rate B. Now we know what is the time requirement. We need the process to be completed in 6 seconds, and we do not know what is the clock rate. This is the question. This is what we need to find out. Correct? This is what we need to find out. But they told that we have got the change in the CPU clock cycles as 1.2 times. So 1.2 times A is already done. So we already have got the result for A, which is nothing but 40 into 10 to the power of 9. So 1.2 into 40 into 10 to the power of 9 by clock rate is equal to 6 seconds. Now I can pull the clock rate here and I can pull this here. When I do the division, I get 8 into 10 to the power of 9 cycles, which is nothing but 8 gigahertz. So the formula is very simple. We need to remember the CPU clock cycles by clock rate, without which things won't work. In this case, what we had is only clock rate and the CPU time. We found out the CPU clock cycles, but in the second case, what we had to find is only the CPU clock rate. Clock rate is the one that we need to find out in the case 2, which is nothing but the speed. First case it was 4 gigahertz. The second case it was 8 gigahertz. Very simple. We found this out through the available data for this. They just gave a simple clue saying that it is 1.2 times the clock cycles. Remember it, 1.2 times A is what they have given. Now do you understand how do we solve it? Very simple. So the answers are going to be 8 gigahertz. That's the answer that you need to understand, and that's how we have arrived at it. The only thing that you need to remember is we need to find the CPU clock cycles, and then we found out the clock rate. Both are very important, and we'll have a lot of problems related to this, and we are going to solve a couple of more problems, probably if not today, at least tomorrow, and that will be very helpful for you. Till now, did you understand this problem, all of you? Another problem, but let's understand that one very important point we need to understand. I am capable of reading a book in 250 pages book in say 3 hours. For instance, I'm just giving you a random number. You might not be capable of reading that in 3 hours. You could finish it faster or you could finish it slow. Do we read in the same time? Do we complete the task at the same time? No, right? Definitely not. You and I are different. I could be slow or I could be faster, and we two are two different people. So the result would come in different times. I could complete it in say 3 hours, and you may need 4 hours for completing the same task. That's what we need to understand. Now I'm going to give you another formula. Just remember this case, and I'm going to use this case as a very important scenario when it comes to the next level. I'm going to use this scenario of the same task being done by two different people at different times. That's what we are going to see, and we will connect this concept. This concept can be connected. Okay, so let's go ahead and understand that. Now, number of clock cycles required for a program is the next formula that we need to remember. In the previous case, what was the formula we wanted to know? We wanted to find out how exactly the CPU execution time can be found. This is the formula that we wanted to go with. Now what are we going to do? We are going to find out the CPU clock cycles. How do you find it out? Very simple. The number of instructions for a program into the average clock cycles per instruction. I have 10 instructions. I need say 0.5 milliseconds for each of the instructions. So 10 into 0.5 is what I need. The number of instructions plus average clock cycle for one instruction will give me total CPU cycle. It's a very simple thing. You have one idli in hand, you eat it in 5 seconds. I give you 10 idlis. How much time do you need to eat? That's exactly what we are talking about. So you need to know how many idlis do you have in the table, how much time you need to eat one idli, and you can get the content very easily. I'm just connecting it with idlis, but it is not idlis, it is going to be instructions here. Let's solve a problem. This is very important, and remember one very fundamental thing. I'm going to tell you again, we two are not the same. I can do the task little faster or little slower, and you may do it little faster or slower than me. We are not going to do the same task in the same time. It is highly impossible or highly improbable that we could be doing that in the same time. So remember that we have two machines are not the same. Right. Now the question is simple. I'm going to take another problem statement and we will sort it out, and with that probably we will conclude the session for the day. I'm also nearing the end of it. Now we have an instruction set called as X. There is an instruction set named X. Now the same instruction set has been implemented with two different architectures. First architecture is called A and the second architecture is called B. Remember, I have got an instruction set called X, and the X can be implemented the way you want. We have got it implemented in two different architectures. One is A, another one is B. The clock cycle time for A is 250 picoseconds, whereas it is 500 picoseconds for B. The CPI, what is CPI? Clocks per instruction. What is it? It is 2.0 here. It is 1.2 here. Remember it. I have got two different variants A and B, where the clock cycle time is 250 and it is 500 here, whereas the CPI is 2 here and it is 1.2. Now I will give you a program. Say it has got 5 lines. This 5 lines of program will be run in both the architectures. Which architecture is going to be faster is the question. That's it. Is it clear, all of you? The question is very simple, where I have got an instruction set. The instruction set is used to write a program. We have written a program now. The program is run on two different implementations of the same instruction set. One is called A, another one is called B. Which is faster or which is slower is the question. Do you understand the question, all of you? I need an acknowledgement before I go to the next slide. Do you understand the question? Good. Let's answer the question right now. It's pretty easy. Please follow it carefully, guys. If you miss it out, I'll explain you once again. It's very important question. Now, remember, the number of instructions are the same for A and B. I told you that, right? Because it is the same program. And did I tell you how many instructions I have? No. I do not know what all the number of instructions I have. So, what I do is I assume it as Z. I do not know the number of instructions, so I assume. I am free to assume, and that's what I have done. Now, Z is nothing but the number of instructions. Right? Now, how do you find the clock cycles? Very simple. Z into 2.0, Z into 1.2, because 2.0 is nothing but the CPI for A, 1.2 is nothing but the CPI for B, and the formula that we have used here is number of instructions into average clock cycle per instruction. So we need to multiply both of them. So I do the right stuff here. Now I calculate CPU clock cycles for A. I calculate the CPU clock cycles for B. So it becomes Z into 2.0, Z into 1.2. Z is nothing but the number of instructions, and I don't care about it really, because I do not know the number. I am just assuming it. So remember, till now what I have done is I have just assumed that the number of instructions are Z, and I multiplied it by 2.0 and 1.2 respectively to arrive at the clock cycles for A and B. Now what is the next step? I need to compare the CPU time. Only when I compare the CPU time for A and B, I will be able to understand if A is faster or B is faster. Do you understand the point? I need to compare the CPU time. CPU time is nothing but the execution time that I am talking about all this time. So how do you compute that? CPU time for A is nothing but the CPU clock cycles for A into clock cycle time for A. This is what I have told you some time back. CPU clock cycles for A into clock cycle time for A. So what is CPU clock cycles for A? I have computed that as Z into 2.0, where I do not have to bother really about Z. Z into 2.0 into 250 picoseconds is the time that is required. So finally, I need 500 Z picoseconds for CPU A. Now I come to CPU B. Z into 1.2 into 500 picoseconds, which will get me 600 Z picoseconds as the result. Now, I told you sometime back that execution time of A by performance of A by performance of B equal to the execution time of B by the execution time of A. So what do we do here? Very simple. 600 into Z picoseconds by 500 into Z picoseconds. So what do we get? We get 1.2. What do you mean by that? Very simple. A will be 1.2 times faster than B. A is always better than B by 1.2 seconds. That's it. It's very simple. Remember it. This formula is the one that I have told you with the same Sachin and Dravid example. There we got Sachin 3 times better than Dravid, thrice better than Dravid. Here I get it as 1.2 times better than B. A is 1.2 times better than B. That's all. We have completed 50% of whatever problems that we had to complete for the day, and we have another 50% left out that I will discuss tomorrow. Is there any doubt till now? Any doubt till now, guys? Yeah, please. Yeah. Yeah. One second.